And here I have a graph that kind of starts out underneath like this, humps, it has a maximum there, it goes through here, a minimum, and then it kind of goes up like this. Now the equation of this graph is y is equal to x cubed plus 3x squared minus 9x. Okay, if you were to put that in your calculator, this is what it would show you. Okay, now I haven't labeled any tick marks here or here. What I'm interested in is the basic shape. Okay, now let me change colors here, and let's plot the derivative. So in order to do that, I'm going to put another graph immediately below this one, like this. And I'm going to put the derivative right underneath it, just so we can kind of compare these two graphs. Now let's take the derivative here. The derivative of this curve, y prime, is the derivative, as we've been talking about. You should be able to do this in your kind of really quickly now. By now we've done so many of these. 3x squared plus 6x minus 9. Make sure that's correct. 3 comes out, 2 in the exponent, 3 times 2 is 6, 1 in the exponent, and then the 9 just kind of hangs along for the ride by itself. Okay, now what would the derivative look like? If you were to plot this function, it would look something like this. Right here at this point, I'm going to explain this to you here in a minute, but I need to make sure I get this stuff lined up or it won't make any sense. The derivative looks something like this. It goes down underneath the x-axis like this. Okay, so it kind of goes up to infinity like this, and it kind of goes through those 2 points. There's a minimum down here, etc. Now, it turns out that just from knowing that, there is a whole lot of information that you can kind of glean from these two graphs. Okay, first thing I would ask you is, if you wanted to sketch this graph, how would you know where this graph, remember this original graph is the one we want to actually sketch. That's the one that they say, give it to you and they say sketch it. So what I'm going to do is I'm going to kind of draw a little, I guess a little divider here, and I'm going to write some properties down, and I'm going to teach you how those properties follow from what we've drawn here. The first thing that you can do in order to sketch a graph is to find the x-axis crossings. Find x-axis crossings. Now how do you do that? This graph is like this, right? And what I'm trying to get you to figure out is, how do you find exactly where it crosses here, where it crosses here, and where it crosses here? Well, the way you find that is, you find it by setting y is equal to 0. Okay? So think about this. This is a graph of y is equal to some function of x, and everywhere it crosses the x-axis, the y value at that point is 0. So here, I'm making up a number here. This might be negative 10, comma 0. So x is equal to negative 10, y is 0. Here, it looks like it's pretty close to x is equal to 0, y is equal to 0. Here, it's around maybe 2 or 3x, and then the y value, again, is 0. So what you would do is you would sit here and you would put a 0 here for y on the left-hand side of the equation, and you would have an equation in x, and that would be equal to 0, and you would solve for x, and you would get 3 values of x because you've got x cubed, and from your algebra you should remember that you would expect to get as many solutions as the highest power in your equation. So you would get 3 values of x, and these values of x would correspond to these. So you could have a big graph that you would have on your test or your problem sheet, and then you could put little dots along the x-axis, and you would know that the graph would go through those points, but you wouldn't really have much idea of the shape of the curve, but you would know that they would have to go through those 3 points somehow. So that's sort of the first thing on the list. You don't have to do this all the time, but it sure does make your plot more accurate if you could solve the equation for y equals 0 and then plot that. Now, we've plotted the first derivative here, and I want to teach you some properties of the first derivative as we go. Notice, if you just sort of think about it here, this graph, okay, this is a derivative, right? This one here, which means this is a representation of the slope of this curve at every value of x and y, okay? So think about it up here, over on this side, okay? On this side, the graph is sloping upward, right? So remember from your algebra, when things slope like this, it's a positive slope. When things slope like this, it's a negative slope. So here, in this region, you have a positive slope. Now look at your derivative, it's positive here. Remember, this, everything above the y equals 0 axis, these are all positive numbers here. So your slope is positive. So this graph is telling you that the curve kind of goes up. So from that, you can learn a couple of additional things. I'm going to write them down here. If the derivative is greater than 0, and look, in this case the derivative is greater than 0, okay? Then that implies, and this is what I mean by this double arrow, that the graph of y itself is increasing. So really, you just look at the derivative, in any place the derivative is greater than 0, that definitely means for sure, without any hesitation, that the original function y is increasing. And look, you can convince yourself of that here. The slope here is positive, and so that means the derivative is positive. And so in these two regions here, definitely the slope is going up, and y is increasing. Also note, look here in this region here, when the graph starts to kind of come down. Well, the slope, it looks like something like this, right? In this region here in the middle. And remember back from your algebra, a slope that kind of goes from upper left to lower right is a negative slope. Okay? Now look in our graph here. In this region right in here, okay, the slope, which is the derivative, is what we're plotting here, is less than 0. It's below the y equals 0 axis. So the slope is 0 in this region everywhere from here to here, and that represents the fact that this function is decreasing in that realm. So what you can learn from that is, if the derivative is less than 0, then that means that y is decreasing. Right? So immediately you can calculate the derivative, and you can look at the different regions where it's increasing and decreasing. I mean, when it's positive and negative, positive and negative, and from that you can immediately figure out what regions your graph is going to be going up and which regions your graph is going to be coming down. Now that's all well and good, but there's one property here of the first derivative that's the most important of any of these, and this is the one that's going to be the most useful to you. And I've kind of danced around it, but look. Your graph is going up here, so that means there's a positive slope, and that means there's a positive slope here. Now your graph is going down here, which means that this is a negative slope, and so this is a negative slope here. Well, right here at the top, when the function bends over, okay, so here's the slope, and we get to the top, the slope goes like this, and the slope moves to the horizontal, and then it comes down, right? The slope begins to come down. Right here at the top, the slope is equal to 0, okay? That means that the slope is equal to 0 anytime you have something reversing course like this. And this is called a local maxima. This is called a local minima. But anytime you have one of these, the slope, which is the slope of the tangent line to the curve, has to be 0 at this point, has to be 0 at this point. So what can you learn from this? If the derivative is equal to 0, okay, what does that mean? That means I have a local max or local minimum. Now look at my derivative. I've shown you that here. In fact, when I drew the graph, I made sure to line up this very top point where the derivative crosses the axis and where the derivative is equal to 0, when y prime is equal to 0. Same thing here. I lined this point up when the derivative is equal to 0. And what does that tell me? At these 2 points, my function reverses course. So I have a local maxima or a local minima. This property is going to be one of the most useful to sketch graphs. Okay, it's going to be one of the most useful to sketch graphs. So let's move on to the second derivative, and we're going to learn a few more properties about it, and then we're going to work a couple problems. Well, more than a couple. We're going to work a few problems. I'm going to draw another graph, again, immediately below this one, right? And this is going to be a graph of the second derivative. Now, from your expert calculus skills that you have, you should be able to calculate the second derivative, which would be the derivative of this function, which would be 6x plus 6. Okay? 3 times 2 is 6. The exponent becomes a 1, and then the 6 just becomes by itself. Derivative of this constant is 0, so I don't even write it down. Okay, this is the second derivative. What does the second derivative represent in big picture terms? It is the slope of the first derivative. Okay, it is a graph that represents how this first derivative is changing, the slope of it. Okay, so what does this function look like? Well, I'm going to line this up here, and I'll tell you why in a second. But it basically is a straight line because, look, this is the equation of a straight line with a slope of positive 6. You should remember that from your algebra. And it goes something like this. Now, let's just take a look at this for a second. Over here, okay, this is kind of sloping upward, right? So this is this is sloping backward, right? So this is a negative slope, and that's why the slope here is negative below the axis here. In this region, the slope is positive, and that's why the second derivative is above 0 at this point. Again, notice right where it reverses course right here, the slope of this curve, which means the derivative of this curve, is 0 at this point. And that is why the second derivative goes through 0 at that point. So you can use that. Now, let's learn from this. Okay, let's learn from this. What you can learn is if the second derivative is greater than 0, then what does that imply? Then the original function y is, and I'm going to explain this term in a minute, concave upward. Okay, and I'm going to give you an example of that. It looks like this. This is what concave upward means. It's just something that goes up like this. This is concave. If you think about concave, it just means something that's curved like this, like a parabola, and it's facing upward. So the open area here is facing upward. So it holds water is another way that the books sometimes explain it. It holds water. So if it rains on this guy, then water fills it up. That's concave upward. Okay. Now, how do we know this is true? When the second derivative, which is this function here, is greater than 0, so from this region here all the way over, everywhere up here, the second derivative is greater than 0, then let's follow this up to the first graph. Looky here, it's concave upward. So look, if we follow this up to here, then from here over, it's concave upward. Now, why does this work? It's not quite so important for you to be able to work your problems why, but if you want to know why, the reason is what we're evaluating here is we're looking at the slope of this graph here. This is the slope, which is the first derivative, and this is the slope of the first derivative itself. So what this graph is predicting is how fast is this slope actually changing. And so in the end, when you back it out, what it's actually predicting is this guy, is it curved kind of like this, or is it curved kind of like this? Because look here, in both of these cases, like up here, you're going to learn in a second, this is concave downward, right? But in this case, on this side of the hump, and also on this side of the hump, in both cases, the slope is actually negative, okay? But in one case, the slope is changing in a way that defines the fact that it's concave downward. In the other case, it's changing in a way that defines that it's concave upward. That may or may not be clear to you. I think the main thing to look at is the example here, which is really showing you that in this region, the second derivative is positive, and so because of that, it's concave upward. The other thing that you can learn from this is that when the second derivative is less than 0, the original function y is concave downward. And an example of that is when it looks like this, okay, concave downward. Okay? And that makes sense because everywhere this function was negative, if you kind of follow it up here, which would be from here over to here, it's concave downward. So that makes sense. Okay? And then the natural question you're going to have is, well, what happens if the second derivative is exactly equal to 0? Look at here, it's right at this point, kind of like right in there. And that is the division between concave upward and concave downward. So when the curve kind of does a little S like that and it kind of begins to bend over and go the other way, that's called an inflection point. Okay, so this is a new word, inflection point. And so you can kind of just think of that as a reflection or an inflection as when the thing starts to kind of turn over. Okay? So these are the properties that you're going to be able to use to basically sketch lots of different graphs. So let's go ahead and do that now. I'm going to erase this. These properties are the ones that are really important for you to be able to do the problems. And I hope that this example has kind of given you a basic background into how to remember these. Okay. So the problem is, on a test or something like that, here you have f of x equals x cubed plus, whoops, it's not plus, it's x cubed minus x. And the problem is graph this, okay? Well, even though I told you that you can get a much more accurate sketch by finding the x-axis crossings, I'm going to not do that, and you're going to see why. It's sort of an optional thing. You don't always have to do that. The first thing that I like to do, okay, is find where these local maxima and local minima occur. Okay, that's going to be really important. So the way we do that is we take the derivative, okay? So over here, I'm going to take the first derivative. The first derivative is equal to, actually what I'm going to do just for space is I'm going to do it right underneath here. The first derivative is what? From this, it should be 3x squared minus 1. And I think you should be able to do that because we've done these problems before. Now, we're not going to use it just yet, but the second derivative, I'm going to go ahead and take it right here so we have them all together. We're going to use it later. What is the second derivative, which would be the derivative of this, which is 6x. So we're going to have all our function and our derivative in one place. Now, let's find out where there's a local maxima or a local minima. So what I need to do is I need to set the derivative equal to 0. So if I take 3x squared minus 1 and set it equal to 0, which is the derivative here, I'm setting it equal to 0. Let's solve for this. 3x squared is equal to 1. Just move the 1 over. And so then x squared is equal to 1/3, right? So then x is equal to plus or minus the square root of 1/3. Okay? And when you put this in a calculator, you'll find that this is roughly plus or minus 0.6. Okay? 0.6. So those are the x values, the values along the x-axis where we have an inflection point. Okay? I'm sorry, not an inflection point. The x values of where we have a local maxima or local minima, which remember is where you have basically any hump or valley like this. But what this is saying is that this would be at 0.6 and this would be at negative 0.6. I have no idea if the graph looks like this, but I know that I have a local maxima or local minima at these points. But that doesn't really help me so much because that tells me the x value, but I have no idea what the y value is, so I can't really plot anything yet. So how do I plot it, or how do I figure it out? Well, I know the x value. I'm going to take this x value, I'm going to stick it into f of x, and I'm going to get the y value. So let's do that. F of 0.6, I'm just plugging in 0.6 into f of x, and I'm going to let you crank through that on your calculator on your own, and you will see that that equals negative 0.384. Okay, that's just a number that comes out. And then when you put negative 0.6, f of negative 0.6, what you will get is a positive 0.384. Now, we're definitely not done yet, but we have enough to get started plotting this thing. So down here at the bottom, I'm going to have a little graph kind of in the corner here. Something like this. So this is x and this is y. This is the graph of f of x, which is what we're trying to sketch in the first place. What we have shown here is this is going to be positive 1, this is going to be negative 1. Up here, this is going to be positive 1, and down here, this is going to be negative 1. Okay? So what we have said is that at x is equal to 0.6, which is just a little bit past half, and negative 0.384, okay? So roughly right around there, at that point, we have either a local maxima or a local minima. Because what this tells me, that I have a local maximum and local minimum at 0.6 comma negative 0.384, and also at negative 0.6 comma positive 0.384. Okay, that's what this information tells me here. So I have another one at negative 0.6, which again is just a little bit past half, and positive 0.384. So I have something there. So pretty much from that information right there, if you know, I mean, I guess it could come down like this, and then it would bend over and come down again, but in order for it to bend down, it would have to have another local maximum there. Really, there's only one way that you can fit this to have a local maxima here and a local minima here. And so the graph is going to end up doing something like this. But in order to prove that, just to put the nail in the coffin, we're going to do a couple more things. Okay, let's find out where there's an inflection point. Let's figure out where y, second derivative of y, is equal to 0. This is the second derivative, so at 6x is equal to 0, I just set this equal to 0. So at x is equal to 0, I know I have an inflection point, and so then I want to find the y value, so f of 0 is, I'm going to plug that into here. I can see right away I'm going to have a 0 here and a 0 here is going to be a 0. So at the point 0, comma 0, I have an inflection point. Which means what? It means that the curve kind of bends over and starts to go the other way. So I submit to you that from this information you have enough to sketch this curve, and so you can prove to yourself that it kind of goes up to a local maxima, bends over like this, and then kind of goes up like that. And that's a sketch, okay? These x values aren't perfect. You know, they're not symmetrical or anything like that. But you know you have a local maxima here, you know you have a local minima here, and the kicker is that you have this inflection point, which is where it starts to change course, and so you know that this is the only shape of the curve. Now, to get accurate values of where the curve crosses the x-axis, you could set your function equal to 0, and you could solve for those. I'm not going to do that here in this problem, but you could do so. Now, if you just wanted to have a triple check to make sure that you were correct, okay, let's look at the second derivative evaluated here at this point. So the second derivative, which is this, evaluated right here where we have this local minima, which would be at 0.6, x is equal to 0.6. What is this equal to? This is equal to 0.6 times 6, right, because that's what I'm plugging in here, is positive 3.6. So what we have shown is that at this point, where this minima here occurs, the second derivative is a positive number. Since the second derivative is a positive number, it's greater than 0, and that tells us that y, the original function, is concave upward. And that proves that we have our graph exactly right, it's concave upward. If you were to put negative 0.6 in here, over here at this point, and evaluate it, you'll get a negative number, and that'll prove to you that it's concave downward, which is exactly what we wanted to prove.
Learn anything at mathandscience.com.